So, good morning. Welcome to Krishna's class. In this talk, we give the technical details of the proof of the result on the completeness of the trigonometric system in L. What we prove is we prove that the trigonometric system, which is an orthonormal system in L2T, is complete or maximal, and this we do as follows. Okay, because you recall one of the results that we have proved, or an equivalence theorem that we have proved, or what you call a characterization of the completeness of the trigonometric system, or the characterization of the completeness of an orthonormal system in a Hilbert space by proving that polynomial, every polynomial, the set of polynomials in the orthonormal system is what you call a tens in L2 in the Hilbert space. So I'll just write down the result. So what we observe is that L2T is a Hilbert space with the inner product Fg given by 1 by 2 pi integral minus pi to pi Ft g bar d dt. And we also define a new set called Pt, script Pt, which is the set of all Pt, where P is a polynomial of the trigonometric system, by which we mean it's a finite linear combination of the trigonometric system. What is the trigonometric system? The trigonometric system is this. This is the one that is e to the power int over the interval 0 to pi. So n. This is the trigonometric system. What we prove is that the collection of all finite linear combinations of the power int form a tens subspace of L2. Okay, and here we use the characterization here. So the completeness of the trigonometric system, that is e to the power int in L2T, is if and only if the system is maximal. Oh, sorry, that's the definition. If and only if the set of all finite linear combination of e to the power int is dense in. So we will use that. Okay. So let me just now what we have is Pt is contained in L2T, and we explore whether it is dense in L2T in terms of the input. Now this is what we want to do. So I just note down the result we are going to use. The result that we are going to use is this: if H is a Hilbert space, and 2n characterization of the completeness of an orthonormal to alpha So what is it that say that the index at A is a complete orthonormal system orthonormal set if and only if the set of finite linear combinations of is dense in the Hilbert space. Okay. So our objective is to prove that e to the power int. So what we have is, let us explore the problem. Problem is that we have to explore the following. With the inner product I have given earlier, and this we know is complete. Therefore, this inner product, the corresponding inner product space is this. This is the inner product. So with this inner product, now this is complete. Therefore, that's a Hilbert space. Okay. Now, e to the power int is a orthonormal that is we have belonging to set. So this is a complete. Now what we assert is that, or what we want to prove that is that this is a complete orthonormal system, and that of course there we use this characterization theorem, and we prove that all finite linear combinations of I put the set of all finite linear combinations of or what you call trigonometric polynomials. Is tensile. So this is what we intend. So once we prove this, because of the equivalence of this, it immediately follows that e to the power int is already a orthonormal set is complete. So that's our stuff. So let us now see how do we work on this. Just we have a complete and a Hilbert. That is that. Now we have this relation. Okay. We have the set of all continuous functions which are periodic on the interval minus infinity plus infinity period 2 pi. Okay. So we have let CT stand for periodic one period complex valued continuous periodic functions on R1 with period 2 pi. Then what we have is this collection is contained in N2. That's setting. I mean not at the moment structurally, and that we need one more line to right. See that on CT we have infinity, and we also use CT norm 2. This is the Hilbert space now. This is the supremum now. Okay. Now CT with supremum now is complete. It's a Banach space. But CT with is not complete. Now you see that CT is the set of all continuous complex value periodic functions on T is a general theorem. This result is there. So we are going to make it. Okay. This is one result. Is dense in L2T in the norm 2. Okay. Now consider PT combination of finite linear combination of e to the power int. That's PT. We shall prove that this is to be that is dense in CT So that is primarily what we want to prove. If we prove the single result, then all the other things that we require will follow. Now this would become a sort of polynomial in the trigonometric system. Okay, so you have the collection of all polynomials in the trigonometric system. That means finite linear combinations of e to the power int. Now this is a smooth collection of elements or functions in CT. CT is all that we assume is CT is elements of CT are continuous. Okay. Now we prove that this is true. Okay. Once we prove this, okay, what do we? So once we prove this, that PT is dense in CT in the norm. Okay, but how do we prove this? Here we for every F belonging to, okay, so we shall use this. So this is the result. So let us see how we work. Assume we have proved that no infinity. Okay, we have proved this. We have proved this. Then we conclude as follows. So we take choose any L2. Now we shall observe that since CT now this is the crucial result that we are using. This is in L2T. There exists for a given epsilon there exists a delta positive. Sorry, there exists a G belonging to CT such that norm of is less than epsilon. This is the density part of the theorem that we are using. Okay, since CT with this norm infinity is dense in L2T. Sorry, CT with norm 2 is dense in L2T. We have this result. Okay, so we have got a G. So given AF, there is a G here such that this is the distance between F and G is less than epsilon by 2 in the L2. Okay. Now what further things that you can have? So F belongs to, G belongs to Now if we have proved this, we have not proved it yet. Then there exists an element P belonging to T such that norm of P minus G is less than epsilon. But now in CT, see, we get this P minus is less than or equal to infinity, and this is less than epsilon. Therefore, we have so we use this result. Pt is dense in Ct, and therefore this property is satisfied, and we have this inequality, and because of this inequality you have this result. Okay, so what is the consequence? Hence norm of f minus p 2 is less than or equal to where of course P belongs to P, where F belongs to Ct, G belongs to, F belongs to L2T, G belongs to Ct, and P belongs to and this is of course less than epsilon by 2 plus thus any element F belonging to L2T can be approximated as closely as you want using a polynomial in trigonometric system. Okay? Approximate as closely as we want by a polynomial in the trigonometric system, which is essentially the finite linear formation in the Consequently, is a maximal or equivalently complete orthonormal system. Linear to linear. And this is what we wanted. Okay, but this is a conditional statement. This is so provided you can prove this. Given G belonging to CT, there is a trigonometric polynomial, a trigonometric, or a finite linear combination of e to the power int, which lies as closely as you want to the given G in CT and in the realm of the suit norm. So that is what you want to. So it requires to prove that given element of epsilon given epsilon positive and f this is what. So this is our attempt to prove this theorem. Now let us see how do we prove this. Okay. Now the rest of the things are technicalities. So this is a strategy. So we will exploit this strategy, and we have already proved it. We could prove this last year. Okay. All the other steps we have explored. So the first part is steps. The first one. Suppose we construct trigonometric polynomials QKT with the following properties. Now each QKT is a finite linear combination of e to the power int. Okay. So what are the properties? The properties that we asked for is that is non-negative for every t belonging to R, 2, 1 upon 2 pi this is equal to 1. And the third property is that if eta k delta is equal to supremum of QKT on the interval delta pi for each delta positive such that limit k tends to 0, limit k tends to infinity of equal to 0. Okay, that means the meaning of the last statement is the following. So on the interval minus pi to pi, take a delta neighborhood of 0 minus delta plus delta. So you consider this one. That means on this portion of the interval and this portion of it. Okay. Here you see that QK are nice function. I mean, they are smooth functions. They are non-negative. You have not proved that you can choose like this. We have to show that you can actually set up functions of this kind. Okay. And such that, see, this is what you prove, that is eta k delta. So on each of these intervals, you have a number eta k delta eta k delta is taken as supremum of, which is equal to supremum of qkt that means on each of these sets, this is the union of disjoint intervals and it is associated with the delta minus delta to delta. Okay. We take the supremum and that supremum is designated by eta k. Okay, right? And what we want to show is that our qk can be chosen such that qk is non-negative. Integral of qk over minus pi to pi divided by 2 pi is equal to 1, and eta k delta as defined here has the property that limit k tends to infinity equal to 0, or what you want to prove is this: for every delta positive, qkt goes to 0 uniformly on minus pi this is what we, so this is the result that we want to do. Oh, okay, this is the construction that, so the strategy is to construct such a function and we will show that such functions exist. So the proof will be eventually complete only after showing that such a set of functions do exist. Okay, so assuming exist, okay, we define pkt upon 2 pi integral minus pi to pi f of, so sort of transform that we take now. This integral is well defined because these are continuous functions and f we are choosing as an element of Ct. Okay, or this is for f belonging to Ct. So for f belonging to Ct, we can construct such an integral, and this integral is well defined and exists. So pk's are well defined. The second step we are working on. Step 2. Step 2. We prove the following. We prove that Ft as k times 2. This is what we want. This is so. You recall that we have assumed that such functions qk exist. We have to eventually show that or demonstrate that such functions do exist. Okay. If so, we define pkt as and prove that such functions have the property that the sup norm of pkt minus ft equals to 0, or in other words, these class of functions give a approximation to f as closely as you want, as k times to infinity. Okay, so this is what we want. So let us give the proof. Now first is technical, right? So let us recall what it is. So pkt is equal to 1 upon 2 pi f of so pkt is given by this for k equal to, this is well defined. This integral is there is no problem. It's a nice continuous function on the interval minus pi to plus pi. Okay. Now you change then we have pkt equal to f p plus s, change s to minus s, and this you can show that this is equal to 1 by 2 pi. It's very simple. Okay. So what happens? This is equal to integral minus pi to pi You get minus pi to pi ds. Just change s to minus s. You change s to minus s, ds will become d minus s, so it will contribute a minus sign, and the limit for minus s will change from pi to plus pi to minus pi, and therefore eventually this is what you end up with. Okay, with the minus sign and this integral, so we interchange again, so it is from minus pi to pi of this. So now what we do is we work on this integral further. We do one more change of variable. Now change then pkt, change here, then pkt would become 1 upon 2 pi integral t pi minus t fs That's a simple change of variable. Now, what we do next is the following. Okay, observe that both f and qk are 2 pi periodic functions. R. Hence, pkt is, see, you have this periodicity. Because of periodicity, you can once again write this shift to any interval minus, particular to the interval minus pi to plus pi. So pkt is equal to 1 upon 2 pi integral minus pi to pi So this result we get. Okay. Now look at what they are. Okay. You know that qk is a trigonometric polynomial. Hence, a and k e to the power I and k. So this is a periodic function again. Okay. Okay. Therefore, it's a periodic function with period 2 pi. So for QKT, see this is QKT is this. Therefore QKT minus S is what you want. So replace by T minus S. So what you get? You get A N K e to the power minus INS into e to the power INT. Okay. So replace T minus S and in the expression for PKT. Okay, then what do you get? Trigonometric. Because you have e to the power INT coming out, and the other part will produce constants. So you get eventually a trigonometric polynomial. Therefore, this is a trigonometric. Okay. So PKT is also a polynomial. That is observation. Now we have to estimate this, the following. So let epsilon positive be. Now you take F belonging to C. F is uniformly continuous on T. Okay. Because T is compact. Hence there exists delta positive such that PKT minus FT absolute value of this is less than or equal to 1 by 2 pi integral minus pi to pi f t minus s minus ft yes. How do we get that? We get this as follows. We get PKT minus this is equal to 1 upon 2 pi integral minus pi to pi ft minus s minus ft and put that this we have. That is the second property that we have assumed for qk we are using. Okay, and therefore you get this because this integral would is essentially will ft and you have pkt otherwise. Okay, and this is true for everything. We have less than or equal to 1 upon 2 pi integral minus pi to pi, that is this integral mod f ft ds. Now we split this as two integrals a1 plus a2, where a1 is the integral on minus delta to delta, and a2 is the integral on minus pi to minus delta union delta to. So we have split this the range of the integration into two parts. One is from minus delta to plus delta, and the other one from minus pi to delta, minus delta union delta to. Okay, you remember that breakup: 0 minus delta delta pi. So this is this part mu a1, and this part mu a2. So two integrals. Now, in a1 is the integral over minus delta to plus delta. Therefore, mod t minus s is certainly less than delta. Therefore, the integral over minus delta to plus delta is less than epsilon times qk. Okay, you look at this. So you have qks a1 is less than qk. This is non-negative, that is there, and you have this part is less than epsilon, because that is the assumption that, not the assumption, That's the inference that you have f is uniformly continuous. We have used that fact. Okay. Therefore, this part would be epsilon times less than epsilon, then the integral. You get this one, and this is qks comes out, and you have 2 pi divided by 2 pi, so that this is what it is. So if you evaluate that integral, this is what it is. Okay. Not the integral. Is less than this. Okay. Consequently, therefore, you have what you have. You get this is epsilon qks, and integral of that will be 1, but you have an epsilon here, so you get this is hence k minus ft or a1. That we get. Now we look at the second integral. In A2, we have qks is less than or equal to eta k delta. This is the assumption 3. Okay. Consequently, we have A2 less than or equal to twice delta. Okay, which you know that since infinity, we have A2 less than epsilon, because you can make this epsilon divided by twice norm of f infinity, okay, by less than epsilon. By choosing k such that epsilon divided by y is this is possible. This is possible because you have eta k going to 0. So if you choose this one less than epsilon divided by so k sufficiently large so that this is less than epsilon. So that you get k2 is also less than epsilon. Okay. Therefore, what do we get? So putting them together, putting these estimates together, which are independent of t, we have so that actually completes the proof. But we have still kept something to be proved, namely that all these proof had been based on the assumption that there exists some q case with the desired three properties that you have. Okay. Now we have to show that. Therefore, to complete the proof, we show that there exists desired properties, three properties. That is the thing to be. How do you? Okay. First thing is choose QK. Make this choice. Okay. Choose QKT in this form. Then you observe the following. Now CK, see, what about this 1 plus cos t by 2? See, this is certainly positive. Okay, so 1 plus greater than or equal to 0. Okay, so that is there. Then CK may be chosen such that 1 upon 2 pi integral minus pi to pi equal to 1. So that fulfills the second criteria. The first criteria is fulfilled by this. The second criteria is fulfilled. Okay. Satisfied, and 2 is by the choice of CK. So 1 and 2 are now satisfied. Now what more is to be proved? So it remains to only to verify three. Okay. Now note that why it is even? Because you change. Okay. You change t to minus t here, you get cos minus t is cos t. So it remains the same. Therefore, you see that qk is even. Okay. qkt is that is satisfied. Okay. Therefore, we have 1 is equal to ck by pi minus pi to pi okay. So what happens? By 2 pi is there. So this is even, therefore this is equal to this one. Since it is even, you see you get this the 2 that you have here, ck by 2 pi, that 2 gets cancelled. Okay. And this is of course greater than, because you split it on the interval minus pi to 0 and 0 to or. Okay. So this is what you get. So this is equal to ck by pi integral 0 to pi so what happens? Sin t is positive here. Okay, therefore but sin t is less than 1 because you have on 0. Okay, and this is less than 1, therefore you get, when you multiply this by sin t and integrate it, you see that this becomes, the inequality would be greater than this one. Okay, so this, we are lowering this part. Now we estimate. Now it is easy to integrate this because this is d of cos t. So you make use of that. Take advantage of that. Yes. Forgotten. So you get this. This is bound between 0 and 1, and therefore you see that this inequality holds. And what about this integral? And this is equal to 2ck divided by, this is easy to estimate. All that, this is very easy to estimate. Okay, because this you can write as d of cos t, the sign change, and then integrate that 1 plus cos t, or you take d of 1 plus cos t. Okay, you can write it that way and then integrate it. So you can easily estimate this, and then it's a simple integration. Decreasing on 0 to pi as k increases, because this term would start lowering its value. Okay, follows that. There is the k is a decreasing function, therefore this is true on which is less than or equal to so qk is a decreasing function, therefore can get this estimate, and this is for 0 less than or equal to delta on this. That's easy to see. Okay, which implies the third statement, because since cos delta is less than over 0 less than Okay. So this result is valid. Okay, right? And consequently, so the result that we wanted to prove has been now completely established. Okay. So we have now we just write down the statement of the theorem. F belonging to C and epsilon positive, then there exists a trigonometric polynomial P such that it's for every real t. So that proves the result. Okay. There, of course, the periodicity is also taken into account in making this statement, because on the interval minus pi to pi we have proved this result, and therefore it is true everywhere on the interval minus infinity plus infinity, because we are assuming both f. We are assuming f is periodic, but we are by construction p's are periodic functions. Period to be. Okay, thank you very much. So that completes the proof of the theorem. Okay. So we have now proved the density of the PT in CT in the soup norm. Now we have the relation between the L2 norm and the soup norm. So we make use of that. So we start with originally a function in L2t. It can be as closely as you want approximated by functions in CT in the L2 norm, and then such a function can be further approximated as closely as you want by a trigonometric polynomial. Okay, in the L infinity norm, which in turn means it is the same estimate that you have in the L2 norm. Therefore, to putting them together as we have done in the beginning, that every function in L2t can be approximated as closely as you want by functions by trigonometric polynomials. Okay, so that completes the proof, and therefore you see that the trigonometric polynomials, or what are called the finite linear combinations of the orthonormal set e to the power int forms a dense subspace of L2t. What is the consequence of that? The consequence of that by the characterization theorem is that the orthonormal polynomials e to the power int for n belonging to z form a complete orthonormal system. Yes. This is what you. So that is the conclusion. Thank you very much.